In this section, we'll be discussing the basic concepts of probability, what they are, how to interpret them, what does it mean to be small, what does it mean to be large. The odds we are not going to be discussing. Odds are very common though in lottery and gambling and have a lot to do with probabilities. So if you are interested in odds, please feel free to go on YouTube and just type in odds and probability, and you can have lots. But in this course, we will not be discussing odds. All right, basic concepts of probability. Let's get some definitions out there first. So the first is an event. And this could be whatever it is that we want the outcome. What do we want the outcome to be of our experiment? So we call that an event. Simple events are events that cannot be broken down into simpler components. Like just it is what it is. Like if you're taking a die and one die and you roll a 5, right? We can't break that down. But if we had 2 die and we wanted to roll a 5, we could break that down, right? Because it could be a 1 and a 4, it could be a 2 and a 3. So simple event, rolling a die and getting a 5. A sample space is that is all the possible simple events that could happen. It's like when we're rolling dice. What are all the possible ways that we could roll dice? We could have double 1s up to double 6s and any combination in between. So that would be the sample space, all those different ways that we could roll the dice. So I have some examples here that may help you. So like if you're having a single birth, right? And you have a girl, that's your event. Your sample space would be either you're going to have a boy or you're going to have a girl. So we have 2 simple events in our sample space. If you have 3 children, say you have 3 kids. You have 2 boys and 1 girl. Now that could have different orders, right? It could be a boy, and then a girl. It could be a boy, a girl, and then a boy. You could have a girl first and then 2 boys. But all of those are simple events that result in 2 boys and 1 girl. Okay? And then I have a list of all the possibilities when you're having 3 kids. You could have 3 boys, you could have 2 boys and a girl, so you can list all those out. Here are some more examples of simple events. Okay, so 1 girl, simple event. 1 boy, simple event, because you can't break that down. If you have 3 births that result in 2 girls and 1 boy, that's a simple event. Right? You can't break that down. I have 2 girls and 1 boy, that's it. That's all I can do. When I'm rolling a die, right? Outcome of 5 is a simple event. But if I say, if I'm rolling a die and the outcome is an even number, well, even could be a 2, it could be a 4, it could be a 6. So that is not a simple event because I could break down even into the actual numbers themselves. If you just say that I have 3 births, the event of 2 boys and 1 girl, that's not a simple event because you could break it down into different ways. So you have to specifically say what the order is of those 3 children, right? If it's 2 girls first, then a boy, if it's a girl, a boy, and then a girl, or if it's a boy first, then 2 girls. You have to, because we could break that down. So here's another, when you have 3 births, the sample space will have 8 different events. So if we went back, this was one of the slides I showed you earlier, right? 3 births, these are all your options here, right? So just saying 2 girls and 1 boy, well, if I have 2 girls and 1 boy, it could be this event, right? It could be this, 2 girls, 1 boy. Could be this event, 2 girls, 1 boy. Could be this event. So it's not so simple to say that I have 2 girls and a boy. You have to actually break it down. Like having 2 girls and 1 boy, all those are simple, but if I just say 2 girls and 1 boy, I don't know the order, that's not a simple event. So it's a little tricky sometimes. Some of the notation that we'll be using, P, capital P, is going to represent a probability. And what you're going to do is you're going to put some parentheses, and then you're going to put your event right here. So the event is going to go inside those probabilities. So that way you don't get it mixed up with percentile. All right, so P sub 25. It's not the 25%. This is P parentheses, your event on the inside, and then an end parentheses. So that denotes the probability of event A occurring. And an event could be an A, it could be a B, it could be a C, it could be anything. So you can use any letter you want to donate that. When it comes to probabilities, if you have, every probability falls between 0 and 1, every single one of them. If you have a probability of 0, that means it does not happen. If you have a probability of 1, that means it always happens. Okay, if you have a probability of 0.5, that means you got a 50-50 chance, right? 50% chance of that happening. So the closer you get to 0, the more unlikely the event comes, and the closer you get to 1, the more likely the event becomes. But you can have a probability of 0, like the probability that I am a boy is 0. I am not a boy. I know that, genetically speaking. And the probability of 1, I'm 100% certain that I am a female. I have XY chromosomes. Like XX chromosomes. I do know this. I do not have XY chromosomes. So these are all things that you can say with 100% certainty or 0% certainty. There are 3 common ways that we can approach looking at probabilities, and it just kind of depends on how your brain works or on the function. My brain, when I first started learning about probabilities, definitely went with this, relative frequency. Like I just looked at the number of times that that event occurred over the number of times that the procedure was repeated. I just looked at the numbers and just did it that way. So that's a very common way that you can do that. But that only approximates your probabilities. It's not always exact. So you have to be, sometimes this is not the best way to go about it. Another way that you could look at probability, the second approach, is called the classical approach. And this is the way we're going to approach it in this class because we're trying to be more formal and use probabilities and use formulas. So our probability of an event, the formula will be S, which would be the different ways that the event can occur, over N, the total number of ways that simple event. So S stands for simple event. So the simple event divided by the number of different ways that simple event could occur. But it's very important that you know that when you're taking the classical approach, every outcome has to be equally as likely. So like if you're having a child, it's equally likely that you could have a boy or a girl, right? You got a 50-50 shot here. So unless you have some kind of knowledge about, the sperm donor and it has more, X's than Y's, and that's the whole thing you got to deal with. But we're going to assume that they are equally likely. Like if you roll a die, the probability of getting a 1, getting a 2, getting 3, it's all the same, right? It's just whatever it lands on. The last is what we call subjective probability. And this is just estimated knowing our knowledge of events. So this is a type that we won't use all that often in this course. We're going to really focus on that classical approach as much as we can. We may need to use some relative frequency approaches for approximations every once in a while because maybe we don't have all the information, but we're mostly going to use the classical approach. Simulations are something that you can do. They're like an experiment, right? We are going to have a simulation where we are going to go through this procedure and do the same thing over and over again to see if we can create the probabilities that we need. And a lot of times you can actually find those probabilities just by doing this simulation yourself. Like rolling die or playing cards, right? Let's just take a deck of cards, shuffle it, and randomly pick a card. I mean, you can go through that whole procedure and find out all those probabilities on your own. When you are rounding, it's really important that you are being very specific and very exact. If you do have to round, which we really don't like, we'd rather have you use fractions instead of using decimals to avoid rounding errors. But if you do have to round, you can just round to 3 significant digits. And that will vary depending on the problem, how many decimal places that is, but 3 significant digits. But I would always use fractions if I were you, to be honest. I use fractions all the time. Unless we're talking about percentages, probability is a percentage, then it makes sense to use decimals. But and there is one other thing that we need to talk about, which is called the law of large numbers. Now, the law of large numbers talks about when you have so many trials. Like if you're talking about 30 million trials, is the outcome of one individual simulation going to be a big deal? No, it's not. When you're talking about 30 million different things, that is going to be nothing. And when we have these large outcomes, we shouldn't assume that they're all equally likely, because that might not be the case. But the actual probability will depend on all kinds of things, like how difficult it is to prepare for the simulation, the difficulty of the task that we're doing. There's all different things that we know. And I'll give you an example of this law of large numbers right here in a second. So this example, how do I find the probability that a commercial airline will crash on any given flight? Obviously, we couldn't calculate that exactly because we don't know, but that we have some data. It says there were about 39 million commercial airline flights in a recent year, and in that same year, only 16 of them crashed. Okay, we can't use the classical approach here, but we can use the relative frequency approach because we do have some data to go off of. So the probability that we will have an airliner crash, so I'm going to put airline crash, using this data that we know about, okay, is 16 flights out of 39 million. So that is going to be a very, very, very tiny number. When I put it in my calculator, this is what I get. 0 point, then 6 zeros, 410. That is the probability. Very, very, very small. Turns out that is actually true. You have a much better chance of getting in a car accident on the way to the airport than you do in the airplane itself. So rest assured, airline travel is still one of the safest methods of air travel. But just important to know that the classical approach can't be used because our outcomes of crashing and not crashing are definitely not equal. Right? If only 16 planes out of the 39 million trips actually crashed, those are not equally likely events. So definitely don't use the classical approach here. The subjective probability approach is good because we can estimate it given recent data. So it's kind of a good thing. Another thing is ghosts. Okay, a Pew Research Center survey randomly selected adults, and they were asked if they had seen or have been in the presence of a ghost. 366 people responded yes, and 1,637 respondents said no. All right, based on these results, find the probability. Now again, that's the important part. Based on these results, not anything else, just on the results that are here. Find the probability that a randomly selected adult says they have seen or been in the presence of a ghost. So first of all, we have to know how many total people we had. So 366 said yes, plus the 1,637 who said no. Add those together. That gives me a total of 2,003. So that's our total of respondents. So we want the probability that a randomly adult, they have seen a ghost. Have seen a ghost. Okay, so that would be the yeses, right? The 366 said they have seen it out of the total, which is 2,003. Again, grab my calculator out. I get 0.183. 3 significant digits, 1, 2, 3. We didn't have a first digit here, so just the 3 decimal places. So what that means, and this is where you get a lot of, especially on the news, they would report that 18.3% of people believe in ghosts. That's not what this is saying at all. What this is saying is that if you randomly choose a person, you have an 18.3% chance that they will have seen a ghost. That does not mean that 18.3% of people believe in ghosts. So be very careful about how these kind of things are represented when they're represented to you on the news, because that's not what they're not saying, that 18.3% of people believe in ghosts. They're saying that if you randomly select a person, you have an 18.3% chance that that person will believe in ghosts. Notice the difference? I know it's a very semantics thing, but it's very important that you understand that difference. All right, in probability, you will often hear us talk about complementary events. Complementary events are denoted, so if A is the simple event, A with a bar over it, A bar, is the likelihood that that event does not occur. Some people used to use a little c, but they changed it to the bar. I'm not sure why, but you may see it denoted different ways in different textbooks. So let me give you an example. We'll just start off right off the bat. Okay, Pew Research Center surveyed 2,002 randomly selected adults. 1,728 of them said that they use the internet. Find the probability that a selected adult does not use the internet. Now there's a couple ways to do this. Personally, I think the easiest way is the total was 202 people. We're going to subtract the number of people who said that they do use the internet, and that should tell us the number of people who don't. So there's 220 people do not use internet. And then from that number, find the probability. So the probability that they do not use the internet, I'm just going to shorten it because I don't feel like writing that whole thing out. So that's 220 over the 2,002 people. Again, put that in a calculator, round to 3 significant digits, so 1, 1, and then 0. So again, that rounding to the 3rd significant digit is important. So this says that we now have the probability that if we should ask any adult, we have an 11%, right? If you want to change this to a percentage, That's 11.0%, right? Move the decimal spot 2 over. So you have an 11% chance that that randomly selected adult will not use the internet. And then you can also use that to figure out, you know, how many people do, right? So like 11% say they don't use the internet. That means that you have a 89% chance that when you ask someone, they will use the internet. So it can tell you a lot of information. Rare events, okay. If under any given assumption that we're making, the probability of a particular event is very, very small, or the observed event occurs significantly less than or significantly greater than what we expect, we conclude that that assumption probably isn't a correct one. So let me give you some examples. I think it's a little bit easier. When you're using probabilities, what you're going to look for is if your number of successes is ridiculously high, or you have a probability that's 0.05 or less, so 5% chance or less. And it's not a rigid 5%, it could be 2%, 1%, but you kind of have to set a line as to somewhere you're going to draw that line about what you consider to be too low or too high. Another thing that you can do if you have a significantly low number of successes in your experiment or your simulation, that's another thing. But again, you're going to have to set that bar. That 5% is not a rigid amount. You can change that bar to be, and usually it's lower. It's either 5%, 4%, 3%, 2.5%, maybe 1%, whatever that happens to be for you and your simulation. So just a quick recap here of everything we talked about in this. Remember, probability is going to be a fraction or a decimal between 0 and 1. Remember, 3 significant digits if you are going to use decimals. The probability of an event that is impossible is 0. The probability of an event that is certain to occur is 1, right? Because 0 corresponds to 0% and 1 corresponds to 100% probability. Remember your notation. If it's just a plain letter, that would be just a simple event. If there's a bar over that letter, that's going to be the complement of that event. That event does not happen. So hopefully that helps you out on the homework. And we will see you back for a little bit more discussion of probability next.